Hi all. So welcome back to the lecture series of linear control system. So today we are going to discuss the term generalized error coefficients. So in the last videos we have discussed the static error constants and its relation between the standard inputs like that. So here we are going to learn the generalized error coefficients. So we know the main drawback in static error coefficient is that it does not show the variation of error with time, and input should be a standard input. Okay, so in the static error coefficients we already learned about that is for step input, ramp input, and for parabolic input what about the static error coefficients. Okay, whether it is 0, constant, and infinity like that. Okay, so in that cases we have to check with the standard inputs only. Okay, but the generalized error coefficients gives the steady state error as a function of time. Okay, so here we are introducing the term generalized error coefficients. Okay, because actually it gives the steady state error as a function of time, and also using the generalized error coefficients, the steady state error can be found for any type of input. Okay, whatever may be the input, we can find the steady state error of the system. Okay, so that's the main advantage of these generalized error coefficients. Okay, and in the previous videos we know that the error signal in S domain, that is E of S. Okay, so E of S can be expressed as R of S by 1 plus G of S into H of S, and here we are splitting the term into two, that is 1 by 1 plus G of S into H of S and R of S. So here the term 1 by 1 plus G of S into H of S is known as we are taking it as F of S, capital F of S. Okay, and some more notations are there, that is we are using in the further derivations, that is small letter E of t will be equal to Laplace inverse of E of S, that is error signal in S. This E of S will be error signal in S domain, this E of t will be the error signal in time domain. Okay, then F of t will be equal to L inverse of S, and R of t is equal to L inverse of R of S, that is input signal. Okay, this is the input signal in time domain. And we know that after some steps and all, we obtain the error. Okay, actually the error signal in time domain, E of t as, okay, this one, that is C0 R of t. Okay, C0 R of t plus C1 into R dot of t plus C2 by 2 factorial into R double dot of t, etc. Okay, so actually here this R dot and R double dot represents the derivatives of our input R of t. Okay, R dot of t will be the first derivative of our input. Okay, that is the actually we can say that d by dt of R of t, we are denoting it as R dot of t. Okay, and this one, that is t square by dt square of R of t. Okay, it is represented as R double dot of t. Okay, so this is the actual representation. Okay, so C0 into R of t plus C1 into R dot of t, etc. Here's the constants C0, C1 and C2 are mainly depending upon the function f of s. Okay, this is the function f of s. So this constants, that is actually the generalized error coefficient C0, C1, C2, mainly depending upon the function f of s. Okay, and we know that this is the representation of the error in time domain. Okay, and for finding the steady state error, we know that using the final value theorem, the ESS, the steady state error will be equal to that is limit t tends to infinity E of t. Okay, that is we can write it as ESS equal to limit t tends to infinity E of t. Okay, so this is the equation. So here we are just substituting the value of E of t in this equation. So we will obtain ESS as ES is equal to limit t tends to infinity. Instead of this E of t, just write the term this one. Okay, instead of this E of t, just write the term, that is R of t into C0 plus R dot of t into C1, like that. Okay, so this is the representation of ESS, that is steady state error in time domain, that is E0 into R of t plus C1 into R dot of t plus C2 by 2 factor into R double dot of t, etc. Okay, so here C0 C1, I have already said that the value of C0 C1 are mainly depending upon the function f of s. So that thus C0 will be equal to limit s tends to 0 f of s, and C1 will be equal to limit s tends to 0 d by ds of f of s. Okay, that is the first derivative of s, and after taking the first derivative of f of s, we have to apply s equal to 0, s tends to 0 here, and C2 will be equal to limit s tends to 0 d square by ds square of s. Okay, so by observing these three equations, we are getting a pattern for finding the constant, generalized error constants for nth time, that is Cn will be equal to limit s tends to 0 d raised to n by ds raised to n, d raised to n by ds raised to n into f of s. Okay, so this is actually about the generalized error coefficients. So normally the equations, that is the equation for ESS, okay, we'll start by this C2, C0, C1, C2, C2. Okay, so while doing the problems, we'll clearly understand actually what is the reason and how we can do that. Okay, so at last there is a relation between this generalized error coefficient and a static error constants. Okay, this is the generalized error coefficients, and the kp, kv, k are the static error constants. So the actual relation between, actually the correlation between these two is C0 is equal to 1 by 1 plus kp, and C1 is equal to 1 by kv, and C2 is equal to 1 by k. Okay, actually the values of this dynamic error coefficients, that is generalized error coefficients, can be used to calculate static error coefficients. Okay, so this is the actual equation for that. So I hope all of you understand the video well. Okay, and about the generalized error coefficient well. So thank you.